Hello, calculus fans, and welcome to Lecture 9, Part 3. We're going to be computing areas today using the Riemann sum method. And here's our first example. Compute the area bounded by the graphs of f of x equal x minus 1 and g of x equal x plus 1. Whenever we do an area problem, what's the first thing that we always do? Graph the bounded area, right? Okay. To get f of x equal x squared minus 1, let's think about this for a minute. This is what the graph of f of x equal x squared looks like. So what about the graph y equals x squared minus 1? To get this graph and this function, don't we just take the y coordinate x squared of every point on this graph and just subtract 1 from it? So the effect that has is that we take the graph of y equals x squared and we just move it down 1 unit. Whoops. There, that looks better. So this is what y equal x squared minus 1 looks like. And g of x, this is just a line of slope 1 that goes through the point 1 on the y-axis. Now I'm going to draw a bigger version of these graphs. Now that I know what they look like. Well, I didn't do this justice, did I? Here's our graph. And I'll say y. I won't say f of x. I'll say y equal x squared minus 1. And this other graph, y equals x plus 1. It has a y-intercept of 1. And it has slope 1. Let's see, are we lucky enough to have this go through the point 2, 3? Let's see. When x equals 2, y is 2 plus 3, son of a gun. It goes through the point 2, 3. So we lucked out. The points of intersection were easy to find. And notice in the statement of the problem, it didn't say find the area bounded by the graphs of f of x and g of x between x equals some value and x equals some other value. As a matter of fact, in this problem, it didn't state the interval over which we were going to compute the area. So what does that mean? If they didn't tell us the interval over which we were to compute the bounded area, that means that these two graphs, by the way they intersect, bound a region. These two graphs bound a region entirely, and that's the region whose area we want to compute. So if we hadn't known where these two graphs intersected, we'd have to figure that out. Now let me finish labeling the graphs. The graph on top is y equals x plus 1. Very, very good. Okay, we graphed the region. And we're going to be using the Riemann sum in this, the Riemann sum approach in this exercise. So now that we know what the region looks like, we know that we're going to take this entire region from right here, x equal -1, to right here, x equal 2. We're going to take this entire region and fill it up with rectangles of width delta x. I'm not going to draw all the rectangles. I'm only going to draw one. But we know, hypothetically, that we're going to fill this region up with rectangles stacked side by side from x equal -1 to x equal 2. My second step, therefore, will be sketch a typical rectangle of width delta x in the bounded region. Okay, here's a typical all-American looking rectangle. This is going to be my ith rectangle, where I can go from I equal 1 to I equal n. This will be my ith rectangle. And this point right here on the x-axis is x sub I, which means since all three of these points lie on the same vertical line, that the x-coordinate of all of these points is going to be x sub I. Now, what is the y-coordinate of this point? Well, this point is a point on the line whose y-coordinate is the x-coordinate plus 1. So the y-coordinate of this point is going to be x sub I plus 1 And now down here, what's the y-coordinate of this point? This point is on the graph where the y-coordinate of every point on the graph is obtained by squaring the x-coordinate and subtracting 1. So I'll take x sub I and square it and subtract 1. I've just drawn my ith rectangle. Hypothetically, this entire region is filled with rectangles. I'm only going to draw one, but I know that in actuality, I'm going to fill this entire region with rectangles. So that leads me to my next step. Partition the interval spanned by the rectangles into subintervals of length delta x. Well, let's see, I'm going to have rectangles going from here all the way over to here. So I'm going to be stacking rectangles side by side from x equal -1 all the way to x equal 2. My rectangles, the first one is going to be right here at x equal -1. The last one's going to be right here at x equal 2. And we're going to have rectangles all the way in between. So I partition the interval spanned by the rectangles into subintervals of length delta x. So each of these subintervals has the same width, and that width is going to be delta x. This is an important step whenever we use the Riemann approach, whether it's areas, volumes, or anything else. Partition the interval spanned by the rectangles into subintervals of width delta x. And we'll find out why this is always an important step before we finish the end of the problem. This step is going to come back and it's going to pay us big dividends. The next step, compute the area of the ith rectangle. Well, let's just draw a picture of that rectangle. And let me throw this marker away. And let me redraw my ith rectangle. The width is delta x. And what about the height? Here's the height. It's a vertical distance. And it's the same distance as the bottom of this rectangle to the top of this rectangle. How do we compute this vertical distance? Don't we take the greater y coordinate and subtract from it the lesser y coordinate? That's exactly how we do it. So this height is going to be the greater y coordinate, x sub I plus 1, minus the lesser y coordinate, that's the height. I have the width of my ith rectangle, I have the height. So the area of the ith rectangle, a sub I, is equal to the height, x sub I plus 1, minus x sub I squared minus 1, times the thickness, or the width, delta x. And let's see, what do we have? Negative x sub I squared plus x sub I, 1 minus a negative 1 is plus 2, times delta x, the height times the width. And now I think we're ready for the next step. Approximate the area by adding the areas of the rectangles. This is the area of the ith rectangle. We have n of them. We're going to add those up. There. We have approximately the area of the bounded region. Now, do you remember what it was that we did to make this exact? We let delta x go to 0, didn't we? And in that case, we get the area exactly. When we let delta x go to 0, magic happens. The summation sign magically turns into an integral sign. The x sub i's magically turn into x's. Whoops. The delta x magically turns into dx. And we have lower and upper limits on the integral sign. Do you remember how we get the upper and lower limits of integration? Think about it. Now, if you said the lower and upper limits of the integral are the endpoints of the interval that we partition into subintervals, you're absolutely right. So this goes from x equal -1 to x equal 2. And now all we have to do is turn the crank and out pops the answer. By the way, this step where we determine the limits of integration tells us why step 3 was important. In step 3, we partitioned the interval that was spanned by the rectangles. Step 3 tells us in advance what the lower and upper limits of the integral are going to be. -1 to 2. Because these are the endpoints of the interval that was partitioned into subintervals. Oh, now all we have to do is turn the crank on this baby. This is going to be our little f of x. And we compute the antiderivative, -x cubed over 3 plus x squared over 2 plus 2x and this is our capital F of x. This can be any antiderivative of little f of x. So we pick the easy way and just pick the antiderivative that doesn't have a constant term. It doesn't have a plus c. Now we just evaluate the antiderivative at the upper limit. And we evaluate the antiderivative at the lower limit. And we subtract one from the other. Let me just make sure I've done this correctly before I go further. I think I have. Yeah, this is 2, 4 over 2. -1/3, take negative that is +1/3, plus 1/2, minus 2. I'm going to keep these two separate. I have 6 minus a -2 is 8. Minus 8/3 minus 1/3, that's minus 9/3 or minus 3. So I have 8 minus 3 is 5. Minus this 1/2 is 9/2, I hope. You know what I think? I think it's time to do another exercise. Okay, another problem, an area problem, and we're going to solve this using the Riemann sum approach. Compute the area of the region bounded by the graphs of f of x equal 2x squared plus 4x plus 1 and g of x equal x squared plus 6x plus 4. And again, they don't tell us compute the area bounded by these two graphs between x equal this and between x equal that. They don't tell us, which means that the intersection of these two graphs completely bounds the region whose area we want to compute. So the first thing we have to do is find the points of intersection of these two graphs. And it's not at all obvious where these two things intersect. At least it's not obvious to me. Here's what we do. When we want to find the points of intersection of two graphs, we set either the x coordinates equal to 0 or the y coordinates equal to 0. And the reason is, where these graphs intersect, at the points where they intersect, their x coordinates and their y coordinates are both equal. So in this case, we'll set the y coordinates equal to one another, and we'll see what that forces x to be. Here's one y coordinate. Here's the other y coordinate that we set them equal. 2x squared plus 4x plus 1 equals x squared plus 6x plus 4. Okay, it's just a quadratic equation. I'll subtract this mess from both sides. 2x squared minus x squared is x squared. 4x minus 6x is negative 2x. 1 minus 4 is negative 3. Let's see, what are the factors of negative 3? I'm guessing plus 1 and minus 3. Let's see if that works. If we multiply, we get plus x. Minus 3x is negative 2x. Yep, we did it right. So at our points of intersection, either x equals negative 1 or x equals 3. I don't know what the y coordinates are, but the y coordinates will be the same for both of these functions because this is where they intersect. So to find the y coordinates, I'll take the simpler of the functions, plug in the x values, and see what I get. G evaluated at x equal negative 1 is negative 1 squared plus 6 times negative 1 plus 4. And let's see, Negative 1 squared is 1, plus 4 is 5, minus 6 is negative 1. Okay. Negative 1, negative 1. Point of intersection. Now let's take the other x value and plug it in. Oops. Did I do that right? I think so. 9 plus 18 is 27, plus 4 is 31. Yee. Maybe I don't want to do this exercise after all. At any rate, we have our 2 points of intersection. Do I know what the graphs look like in between? In between x equal negative 1 and x equal 3, do I know which graph is greater? Not really. But I do know where they intersect. I'll take that and run with it. I guess really to find out what graph is on top and what graph is on the bottom, we just need to know the coordinates of these two functions at some point in between negative 1 and x equal 3. And I guess the no-brainer is to find out what they're equal to for x equals 0. Okay, we have the y-intercepts of these two graphs, and the y-intercept of G is greater than the y-intercept of F. So between x equal negative 1 and x equal negative 3, G of x is the greater function. And I think that's all that I really need to graph these functions. They're both parabolas, and the leading coefficients are positive, so they both open up this way. Here's one point of intersection. The other point occurs at x equal 3 and y is 31. I'm going to have to draw the y coordinates a bit out of scale. I'm going to have to use a different vertical scale I'm going to have to use a vertical scale that's compressed compared to my horizontal scale. So I will say that this is y equal 31. Here's the point 331. Holy moly. And you'll have to excuse this graph. Somebody dropped it on its head when it was a baby. Okay. There's my 31. And here's the point 0.04 for F. And here's the point 0.01 for G. Or vice versa, rather. Here's the point 0.01 for F. Here's the point 0.04 for G. Holy moly. Let's see, x squared plus 4x. Is that right? X squared plus 6x plus 4. Okay. It's an ugly graph, but it's good enough. We got them graphed. We know which function is the larger and which is the smaller over the interval. Step 2. Inscribe a rectangle of width delta x, and I think last time we called this a typical rectangle of width delta x. So the information that this rectangle gives us is going to be applicable to every single rectangle in that interval. Okay, this looks like a pretty average run-of-the-mill rectangle. And it has a width of delta x the x coordinate on the bottom is x sub I, and the y coordinate will be this thing evaluated at x sub I, 2x sub I squared plus 4x sub I plus 1. And here, the x coordinate again is x sub I. The y coordinate is this function evaluated at x sub I squared plus 6x sub I plus 4. And notice something. We only draw one rectangle, but this whole region is going to be filled with rectangles stacked side by side. So we'll have a rectangle here, and a rectangle here, rectangle here, and so forth. And here a rectangle, there a rectangle, everywhere a rectangle. We're going to have a rectangle here, and so forth and so on. This whole region, this whole crescent is going to be filled with rectangles stacked side by side. We don't draw them in, but we know they're going to be there. Next step, partition the interval that's spanned by the rectangles into subintervals of width delta x. And we're going to have rectangles starting here at x equal -1, all the way over here to where x is 3. So this is the interval that we partition into subintervals of length delta x. Or compute the area of the ith rectangle. You know what? I'm going to zoom in right here and blow this up. Here's my rectangle. Here's the bottom. X of I, 2x of I squared plus 4x of I plus 1. On top, we have x of I, and what else? X of I squared plus 6x of I plus 4. And let me see if I wrote that correctly. I did. The width of this guy that's the width, delta x. What we don't know about this rectangle yet is the height. This is a vertical distance, so the height is just the difference of the two y coordinates. The greater y coordinate minus the lesser y coordinate. So that's going to be xi squared plus 6xi plus 4, the greater y coordinate, minus the lesser y coordinate, 2xi squared plus 4xi plus 1. That's the height. And let me just write all of this down up here. The area of the ith rectangle is the height, the greater x coordinate, minus the lesser, the height, the greater y coordinate, minus the lesser y coordinate times the width delta x. And let's simplify that mess. X sub I squared minus 2x sub I squared is negative x sub I squared. 6x sub I minus 4x sub I is 2x sub I. And 4 minus 1 is 3. So when we simplify the height, this is what it is. Let's see, approximate the area of the bounded region. We know that in reality we have this entire region filled with rectangles. We're going to add the areas of all of these rectangles to approximate the area. Okay, it's time to pull the ripcord. Let delta x go to 0. And in this case, we get exactly the area. It's no longer an approximation, it's the exact area. And this is where the magic happens. The summation sign becomes an integral. The x sub i's become x's. Delta x becomes dx. And this integral, it's a definite integral. So we should have a lower limit and an upper limit of integration. How do we know what those are? Where do they come from? Do we remember? Way back in step 3, we partitioned the interval that was spanned by the rectangles. And that interval went from x equal negative 1 to x equal 3. The limits of integration are always going to be the endpoints of the interval that we partition into subintervals. Okay, let's integrate this son of a gun. Minus x cubed over 3 plus x squared plus 3x from x equal negative 1 to x equal 3. This is our antiderivative evaluated at 3. and we subtract the antiderivative evaluated at -1. Holy moly, what do we get? 27 divided by 3 is 9 minus, whoops, -1 cubed here. That's -1 over 3 times -1 is plus 1/3. Wait a minute. Okay. Before I go any further, let me check something. Yeah, I think I'm okay. -1/3, I got a negative sign out front. That'll make this a positive 1/3 plus -1 squared minus 3 -9 and +9, they wipe each other out. 1 minus 3 is -2. So what do I have? I have 9 minus a -2, that's 11, minus 1/3. We need to do one more, and we need to throw a little twist in there as well. Okay, this has a little bit of a twist. Compute the area bounded by the graphs of x equal y minus 1. I'm sorry, x equal y squared minus 1 and x equal y minus 1. And again, they don't say compute the area between x equal this and x equal that. So the assumption is that these two graphs, as they intersect, form the bounded region or define the bounded region completely. So we'll look for the points of intersection. Where the graphs intersect, the x values will be the same. The y values will be the same. So to find the points of intersection, we assume that we're at a point of intersection. And that means that in this case, the x values are going to have to be the same. And we'll see what that forces the y values to be. So this time we'll set the x values equal to one another. And we have x equal y squared minus 1 equal x equal y minus 1. And we'll subtract y minus 1 from both sides. -1 minus a -1 is 0. Okay. So at our points of intersection, y is 0 or y will be 1. When y equals 0, x equals -1. And when y equals 1, we have 1 squared minus 1 is 0. So when y equals 1, x is 0. Ah, good. And we know what these things are supposed to look like. This is a parabola, and since x is a function of y, it opens up sideways, opening up in the positive x direction. And this is just a line. So this shouldn't be hard to graph. Graph the bounded region, okay. You know what? If I have x equal y squared, that's what it looks like. So to get x equal y squared minus 1, I take this graph and I subtract 1 from the x coordinate of every point. If I subtract 1 from the x coordinate, I'll take the x coordinate y squared and subtract 1. I'm subtracting 1 from the x coordinate of every point on this graph. That moves the graph to the left 1 unit. So this point of intersection actually turns out to be the vertex of the parabola. Son of a gun. We've got the graph of x equal y squared minus 1 plotted. And this thing is just a line. And guess what? We know 2 points on the line, so how hard can the line be to draw? Here's that bounded region right here. And now that I know what this graph looks like, I'm going to draw it one more time just so I can get a really good picture to work with. Whoops. This is the bounded region. And this is going to be x equal y squared minus 1. This will be x equal, what is that? Y minus 1? I think so. I got my graph. And since everything is given in terms of x being a function of y, I'm going to draw my rectangles this way. Now, could I have rewritten this as y being a function of x? And could I have rewritten this as y being a function of x? Absolutely. For the sake of illustration, I chose not to, because sometimes we may have to integrate in terms of y whether we want to or not. And so we might as well learn how to do it now. Let's see, this point is on the y-axis. So this is going to be y sub I on the y-axis. And the coordinates of this point, y sub I will be the y coordinate. And since this point is on the line given by the equation x equals y minus 1, the x coordinate will be y sub I minus 1. And what about here? Again, the y coordinate will be y sub I. And since this point is on the graph x equals y squared minus 1, the x coordinate will be y sub I squared minus 1. I've sketched my rectangle. Now the third step. We only drew one rectangle, but we know we're going to have rectangles filling up this entire region. And we're going to have a rectangle here, and a rectangle here, and so on. We're going to stack rectangles one on top of the other all the way up to here and all the way down to here. So we're going to have rectangles from here all the way up to here. And the interval on the y-axis that corresponds to the region spanned by the rectangles is the interval that goes from 0 all the way up to 1. And from our previous examples, we know why that's important. The endpoints of this interval that we partition into subintervals are going to turn out to be the lower and upper limits of our integral. Next step, compute the area of the ith rectangle. The width is going to be delta y, and the length is going to be, since this is a horizontal distance, the difference of the x coordinates. The greater x coordinate will be farthest to the right. So we'll have the greater x coordinate minus the lesser x coordinate. The greater x coordinate, y sub I minus 1. The lesser x coordinate, x sub I squared, y sub I squared minus 1. Greater x coordinate minus lesser x coordinate times the width, and that's delta y. Whoops. Y sub I minus y sub I squared, negative 1 minus a negative 1 is 0. Okay. Well, I'll take that. That worked out kind of easy. There's the area of our ith rectangle. We approximate the area of the bounded region by adding the areas of the rectangles. This is what the area of the ith rectangle is. Now we're going to add them all up. This is the area of the ith rectangle. And we add up the areas of the rectangles from I equal 1 to I equal n. And we get an approximation. What do we do to make that approximation exact? Let delta y go to 0. We're computing the limit of a Riemann sum. Magic happens. The summation sign turns into an integral sign. The y sub i's turn into y's. And delta y turns into dy. And this is a definite integral, which means we have to have a lower limit and an upper limit. How do we get those limits of integration? We go back to step 3, and we look at the interval that we partitioned into subintervals. That interval goes from y equals 0 to y equal 1. And we compute the antiderivative. We plug in the upper limit. We plug in the lower limit. And what does that give us? It gives us 1/2 minus 1/3, which is 1/6. Voila, we have our area.